All right, so I have now offline, so that you don't have to waste time watching me write, I have written down the pseudocode for our merge function. And let's briefly walk through this and just see how this works. So recall the merge function is being used as a subroutine in the Mergesort algorithm. And the way merge is supposed to work is it's supposed to take in two sorted arrays as inputs and return those two sorted arrays merged together into a single sorted array. Okay, so input is sorted arrays, output is sorted array with all the same values. Okay, so first what we do is we initialize an output array. So I'll do all my comments in red here. So D is our output array. We'll have three counters that we'll initialize, I, J, and K. Right? These counters, they're kind of superfluous, but at least we've got them. So we're being careful with our bookkeeping. Well, in particular, the K is superfluous, but I is going to be our B counter. And so what is B? B is the first input argument here, the first input array. J is our C counter, and then K is our D counter. Our output array counter. So the way this algorithm is going to work is it's going to one by one pull an element from one of the two input arrays and put it in the output array. And then when it does that, it'll increment that input array's counter and increment the output array's counter. Okay, so what are the two input array counters? Well, they're I and J, and we're saying here, while we haven't gotten to the end of either of the input arrays, we'll keep on doing this, right? We'll keep on looking for stuff. So basically what we're going to do is we're going to say if the place we are in B is less than the place we are in C, then that means that the next thing that needs to go into our output array is from B. Right? So if you think about it like this, we've got 5, 7, 9, say that's B, and C is 1, 6, 10. Then the way this is going to work is it's going to initialize both of its counters here. So it'll initialize there and there. And then at every step, it'll compare this element with this element, right? The element at counter I and the element at counter J, and say whichever one is smaller, I'm going to copy into D. Okay, so what this will do is here back in our pseudocode, if the thing if where we are in B is less than where we are in C, then we'll copy B in. Otherwise, we'll copy C in. Right? And so in the example I've written here, the place we are in C is less than the place we are in B, so we copy the thing from C. So we take this and we copy that into D. So D then would be 1, and then we would increment the counter associated with whichever array we just copied something out of. So we'd increment this counter, and then we'd be sitting here at 6. So then the while loop would tick after we incremented our counter for D. All right, after we incremented this counter, the while loop ticks, and so that puts us here, and it says, okay, now let's find the second thing that belongs in D. To find it, we need to compare the two places where we are in B and C, copy in the smaller one. Okay, so this is all it's doing. It's just saying, I'm going to compare 5 and 6, whichever one's less, I'm going to put in here, and then I'll increment up here. Right, and so then in the next step, I'm going to compare 6 and 7. I'll compare the elements of the two places where we are in these two input arrays. 6 is less, so I'll copy in 6. Right, so there's my 6. And then I'll increment my counter here in the C array and take us up to, that'll be looking at 10. And so then what we'll do is we'll say I'm going to copy in the thing that's smaller between 7 and 10, and the thing that's smaller is 7. And then I'll increment my counter here. So now I'm looking at 9 and 10, and I'll copy in the thing that's smaller, which is 9, so I'll copy in 9. And then what's happened? Well, then I've exhausted one of my arrays. So I just let my B counter, right, my I let it get all the way up to P. So in my last increment of I made it so that I equaled the length of B, right, which would break that while loop. So once the while loop is broken, what do we know? We know that one of the two input arrays was just emptied. right? We don't necessarily know how many things are left in the other array, but we do know that the other array needs to have all of its remaining elements copied directly into the D array. So in this particular example, there's only one thing left in the other array. There's only one thing left in C, so it just gets copied in as a single element. But it could have been, right? There's no reason that we couldn't have had a bunch more things up here, right? We could have had 11, 12, and so on. And all of those then would have been copied in bulk down here into the D array. Okay, and so that's what the last two lines in the pseudocode are doing. That's what these two lines are doing. They're just saying if there's anything left, well, there's guaranteed to be something left, but it's just saying find the array that has something left in it and copy whatever is left into D. We know that we know that both B and C are sorted, right? This is a requirement for this algorithm to work, is that B and C are both sorted. So we don't have to worry about checking to make sure they're sorted. We can just copy them directly in. Okay, so the question then is what is the complexity of the merge function, right? So our question is, what is the complexity? Oh, and notice, I'll just mention this if in case it's not obvious. There's no return statement in merge, right? Merge just does a bunch of stuff and then stops. And so the interpretation here is that the merge function, actually I guess it does actually need a return statement in this particular formulation. Yeah, since we're doing merge sort recursively. So at the very end we return D, right? So there's our return statement. So never mind, this does require a return statement. Because in the merge sort function, we are expecting something to be returned, right? We're expecting this thing to have a value. All right, so the merge function does all this. The question is, what's the complexity? So it's clearly an iterative algorithm, right? It's implemented via loops, but none of them are for loops, right? We're really good at thinking about how for loops can be translated directly into the summations. But here, there's no for loop. So what's going on? What else can we look at here to try to determine what is the actual complexity of this algorithm? Well, we might as well go through methodically and think about our program for analysis. And what's our first step in the program? Well, it's to determine an input size. So what's our input size? Well, here it's fair to think about the input size as being the combined size of the two input arrays. Or alternatively, you could think of it as the size of the output array. So that means it is P plus Q, okay? Where P is the size of the B input array, and Q is the size of the C input array. And then P plus Q, that's the length of the output array. So our input size is going to be P plus Q. And then what's question 2 is what's the basic operation? Basic op. So there's a couple candidates here. You could think of it as the comparison, right? Comparisons are always a decent basic operation. You could think of it as a copy. If you have really poorly implemented primitives in your programming language, you could think of it as an index or as an index increment or something like that. But probably copy or comparison are going to be the safe ones. And in fact, note that the comparison happens every single time the while loop ticks. Right? Right after the while loop is instantiated, the first thing is that if. Right? So the if has to happen every single time the while loop ticks. So let's go ahead and use the comparison as our basic operation. So it's B at index I is less than or equal to C at index J. Right? That's our basic operation here. So the question is, how many times can that fire? Right? How many basic operations can we get as a function of the combined size of the two input arrays? Well, we'd really like to be able to just write a summation, right, using for loop limits, but we don't have a for loop, so what else can we do? Well, I invite you to notice the following fact. Every time the while loop ticks, we increment the k counter. How large can the k counter get? Well, it's limited by the structure of the algorithm. It's limited to p plus q. So we know that no matter what happens, k can never be larger than p plus q, right? So we can't write a sum easily, but we can say that, so the question here is, how many, essentially what is C of n, right? What is the combined time for our merge sort algorithm? So what is C of n? So note that k starts at 0, increments every time the basic operation occurs, and can't ever get larger than p plus q. So k is always less than or equal to p plus q, and increments exactly one time for every basic operation, once per basic op. Okay, so we can use that to infer that the algorithm can never make more basic operations than p plus q, which makes sense, right? If you think about this, all we have to do is look at each element one time, right? There's never any reason to look at an element again after it's been copied into the D array, right? Once we copy an element in, we're done with that element. So each element gets at most one experience of being compared to another element, right? So what that means is that the total number of basic operations can never exceed p plus q. Okay, so that means C of n is always less than or equal to p plus q. Right. So now I've written this as C of n, and then there's these p plus q, which is a little bit strange. What's p plus q? That's just the size of the output array. So now let's look back to Mergesort and see where the size of merge's output array appears. So here we have Mergesort is what it's doing is it says let's cut the array in half, and then let's go merge both sorted halves. And so, if I'm trying to sort an array of size n, and then I call merge on the two halves of that length n array, then the total length of the output from merge is just n, right? So every time merge sort is executed, the merge function runs at most n steps, right? So what does this mean? So this means that C of n, now referencing the n from Mergesort, C of n can be thought of as a linear time algorithm. So it's a big theta of n. And so if we scroll all the way back to our question here, where we said, let's hypothetically imagine what we could get out of Mergesort if the merge function were linear time, and we said we'd get this n log n. Well, we just showed that the merge function is linear time. So there we go. We're done. So all of this suffices to show, this combined with the analysis we did last time on the hypothetical merge sort, all of this suffices to show that merge sort is an n log n time algorithm, right? So because of this, and I'll just recap the whole analysis here. Because of this, we have merge sort looking like this. T of n equals 2t of n over 2 plus the splitting time plus the combining time. The splitting time is constant, so this is 2t of n over 2 plus something constant time plus something linear time. And because this whole piece together is linear time, then that means that t of n altogether is big theta of n log n by the master theorem. And that completes the analysis of merge sort.